Hey guys, how's it going? Welcome to the Auckland Game Developer Meetup for this month. This is definitely something new for me, sort of trying to do it live. So we'll see how we go. And today we're going to talk about optimization for VR, specifically mobile VR. So we'll get started. The people who will benefit from this talk most is sort of anyone sort of developing for mobile platforms. Everything in this talk will scale like really well for if you're developing sort of a mobile app. So we'll sort of talk about setting up the project, what artists need to keep in mind when creating their art assets, some of the sort of optimizations that we do specifically for VR, and other optimizations that work just on general mobile platforms. How to do profiling and sort of what the optimization sort of loop cycle looks like. Some bonus optimizations that I haven't really used in projects, but I've learned from looking at other talks and other things in the industry. And then questions and answers if anyone has any questions about their specific project or wonders if I've dealt with any problems, then we'll go over that. And if you have any questions throughout the presentation, just feel free to ask, and I might come to them when we get them, or I'll come to them at the end. A little bit about me. I've been a hobbyist game developer since 2013, starting with X&A's, which was like Microsoft's old Xbox developer framework. Started using Unity in early 2016. And I worked for a few different jobs, working for a bioinformatics company that worked with DNA. So it's quite interesting to see now that we're in a pandemic, sort of seeing all the databases and stuff being used that I actually was also working on back then. Did a bunch of GPU programming with CUDA. And then in 2018, I got my first job using Unity. And that was for a company in Hamilton called Company X. And we created training apps for Customs New Zealand, as well as one of the gas pipe companies in the country. And now I work for a company in Australia named Situ Systems that allows you to sort of walk around your house before you build it. So Situ Systems, the whole selling point at the moment is sort of builders have these raw, what they call IFC files, which you create in Autodesk Revit or ArchiCAD, and we convert these to 3D interactive homes in less than 1 minute. And these files, they're super basic. They don't have any carpet. They don't have any furniture in them. They're just sort of the walls, sort of bench tops, and there's no sort of like super visualization there. So we also partner with suppliers. So we actually put real ovens, real bench tops, real paints, real flooring, real tiles into these houses. So I'll quickly show you a quick demo of what our main product is at the moment. So you can sort of walk around this house with panoramas, and this works on mobile or PC. And we're just sort of now starting to deep dive into VR, which is going to be sort of our next product. So let's have a look at the hardware we're using today. So I'm only really going to be talking about the Oculus Quest today, but these other two headsets, the Vive Focus 3, which is sort of like a more professional business headset, and then in the bottom right hand corner, the Pico Neo. Everything is super relevant to them. In fact, all three of these headsets share the exact same processing chip, so they're pretty much the exact same computer, just with different cameras, different screens, different lenses, and different controllers. So what is the Oculus Quest 2? It's a super cheap VR headset. It's by far, I think, the cheapest way to get into VR now, other than Google Cardboard. It's 570 New Zealand dollars for the headset. The resolution of the headset's super high. It's higher than sort of anything really that came before it, pretty much. Like it's higher than the HTC Vive and Vive Pro. It's got 6 gigabytes of shared memory between the GPU and the CPU, and it comes in 3 different storage configurations. But now the 64 gigabyte version has been removed, and there's just the 128, which they sell for the same price as what was the 64 gigabyte. The chip that's powering it, the Snapdragon XR2, is actually a variant of the Snapdragon 865 that was seen in phones 1 to 2 years ago. So it's got the exact, it's pretty much the same processor what's in a Samsung Galaxy S20 or a OnePlus 8. So that sort of brings you to what I'm going to call is sort of the main challenge of developing for mobile VR. If you see sort of up here, we've got sort of Fortnite running on a Samsung Galaxy S20. So there's much more pixels on the Oculus Quest compared. So even to run at sort of what I call the minimum frame rate for VR, which is required for publishing, it's already 83% more pixels per second. So the sort of graph showing you here is sort of like sort of nausea levels. Like for VR, frame rate is just so much more important than for any other platform that's come before it. Like you don't want to have stutters. Stutters and lag just cause people to get sick. At 60 frames per second, it's quite interesting because most users, they won't notice the lag, but you'll see that once they take off the headset, quite often they're looking quite pale and they look quite sick, but they won't actually notice themselves getting sick. So ideally, I always like to target 90 frames per second. And the Oculus Quest 2 for a recent update can now go all the way up to 120 frames per second. And you can see that's requiring roughly 3 times the performance. It's not an exact conversion because it's not, the render pipeline sort of has 2 stages. One where you've got sort of the fragments, which is sort of like the vertices of the models getting passed through, and then it's the pixels. So it's not a direct comparison, but it's roughly 3 times the amount of frames that you're having to deliver if you want to get that frame rate. So let's have a look at how sort of we set up the Unity project. So I'm going to talk about 3 things to start with, sort of, which these are sort of really big decisions that take a long time to change. Sort of choosing a version of Unity to use, choosing a render pipeline. If any of you guys are Unity developers, you'll know that we've sort of been in this render pipeline hell for 1 to 2 years, where it's quite hard to decide what render pipeline you should use. It's sort of one of those new things that Unity's added, where the new thing's better, but it's missing features. So do you want to have like the old thing that's complete or the new shiny thing that's somewhat incomplete? And then we'll talk about choosing a VR framework. So Unity has sort of 2 main types of releases. They have these LTS releases, which stands for long-term support. And these are supported, I think these are supported for 2 years. I think that's a mistake in my slide. They're supported for 2 years with bug fixes, and they release 1 of these per year. Then they've got these 2 stable tech releases, which are slightly less stable. And they release two of these per year now. There's also beta and alpha releases, but I really think you should avoid these if you can for developing anything going into production. I have this sort of simplified graph that's sort of how I decide what version of Unity to use. So the first question I ask myself is there some specific feature that is only available in a tech release or a beta release that I need for my application? So one of the tricky things of these VR headsets is they're constantly evolving. Like the Oculus Quest has just announced in like the last 2 days that they've added a new feature where you can actually see like people and like cats and dogs sort of walking into your VR space. Like they'll project like the sort of hologram into it. And the Quest has been this platform that's just kept on adding and adding features, and sometimes these features are only available in a tech release, so sometimes you have to use that. But if you can use an LTS version and it's been out for more than 4 months, then I would use the latest LTS version. This slide also sort of shows sort of how I like to do development in terms of upgrading versions. So like if you're on an LTS, then hopefully you should just be able to stay on LTS versions and slowly upgrade. And if you're on a tech release, then your path should be hopefully getting to an LTS version for production. So now I'll talk about choosing a render pipeline. So there's three choices for render pipeline. There's the old render pipeline, which is normally referred to as the built-in render pipeline. Then there's the two new render pipelines called the universal render pipeline and the high definition render pipeline. I guess there's also another one, which is the scriptable render pipeline, which is you can fully build your own render pipeline from the ground up. I don't really know of anyone who's doing it, but that is now an option of Unity. So comparing the universal render pipeline against the built-in render pipeline, it's generally got better performance. It has this new thing called shader graph, which lets you create shaders visually rather than having to write the code out manually. So that's really nice. It's configurable and customizable. There's sort of like all these web hooks C# hooks where you can sort of interrupt the pipeline at stages and add stuff in. It's going to continue to be supported in the future. Like they're sort of slowly killing off the built-in render pipeline. And you now can get GPU-based particles, so they will run much more performantly on devices like the Quest. The real downsides of using the universal render pipeline is a lot of assets aren't built for it. Like if you use Unity's XR interaction toolkit, I believe it, like all their samples actually still use the old render pipeline, so you have to click the upgrade button. A lot of the assets on the Unity asset store are still using built-in render pipeline, and there's still some features that are missing. So they have this page here which shows all a full comparison between the built-in render pipeline and the universal render pipeline, and it's really long, and there are still some things missing. Most of the things that are missing, the community has added back in if you're happy to buy an asset off the Unity asset store. This is one of the assets that I've played around a little bit with in my spare time, which is just sort of like this essential shader pack. It adds things from the HD render pipeline back down to sort of the universal render pipeline. So it adds things like skin shaders if you want to have things like subsurface scattering of light. Has custom hair shaders, cloth shaders, Toon if you want to sort of make like sort of an anime sort of graphic style game or something like Borderlands, and a whole bunch of other useful features. So I definitely would check that out if you feel like there's some things missing in URP. So that leads us to our sort of final major project choice, which is choosing a VR/XR framework. I don't really like any of them. They're all getting there. They're all very close to being like how I want them. And I think given another year or two, I think VR will be a lot easier to develop for than it is today. So yeah, I'll quickly go over sort of all the frameworks. Steamvr. This framework's actually quite old. It's about 3 or 4 years old, and I think it's by far the most perfect framework. It has really good samples. It has it allows you to see sort of your hands in VR, which is quite a tricky thing to get right. It lets you see the controllers and sort of give controller hints. But the downside is that if you want to develop for a standalone headset like the Oculus Quest, it only works on Steam, so it's not going to work at all. So that's kind of a big blocker for this project. Next is the Unity XR interaction toolkit, which is what which is what I use for this project. It works on all the major headsets. It's you sort of have to hack it a little bit to get Steamvr into it, which is kind of average-ish. Steam's working on making a native like sort of layer into it, but I've been using it for all my development, and it's really good. The only problems with it is it's pretty bare bones. It sort of just gives you input, track controllers, and a headset. It doesn't have like sort of native VR hands. It doesn't have like guns if you're wanting to make like a shooting game. Doesn't have things like VR climbing, which is where the next one sort of comes in, which is like sort of Unity asset store frameworks where the people on the asset store are creating these frameworks that have everything built in. Like they have like climbing, they have guns, they have bows, they have all these features that you want in sort of your VR game, and you can just drag and drop them. The only main downside with these is that you sort of have to learn the code base, and you have to trust that they're stable. If I was developing a game, I definitely would use one of these, probably, at least as a starting point. The other option is to just use native VR frameworks. Back when VR was first coming out, this was sort of like your only option, and you had to download every single framework for each headset and sort of duplicate your project and sort of have this really hacky project to compile down to each headset. And luckily, we're past those days. If you're just developing for Oculus and you have no plans on releasing on Steam and whatnot, then it's a really good option. There's really good support. Yeah. So now we'll start talking about sort of some of the specific Unity settings to get more performance. So this is probably the easiest performance gain, which is multi-view. So essentially, there's two sort of ways for Unity to render a VR scene. One is using what's called multipass, where it sort of gets two individual cameras and renders them completely separately. Or there's multi-view, which just sort of has like one camera and then sort of transforms the point so that it doesn't have to do sort of the looking at vertices separate in two separate steps. So you get like a 20 to 30% performance boost, I think, on the sort of CPU side. You want to set your compression textures to ASTC texture compression, and this should just be done if you're developing for any mobile platform like Android or iOS. You're copying less memory to and from the GPU, which means faster GPU copies. You get a smaller APK size, or sort of compiled binary size. And there's a picture that I got from NVIDIA's website sort of comparing the two, and you can sort of see that there's like a little bit more detail in some of the specs, and like some of the curves look a little bit better in the uncompressed, but unless you're like really, really close to textures, you're not going to see the difference at all. Light and shadow settings. Ideally, you want to have as little lighting calculations as possible. So universal render pipeline lets you sort of choose between per vertex and per pixel. Ideally, you have vertex lighting. This can sort of create some artifacts if your vertices are super far away on your models. So that's something to keep in mind. Maybe to counteract this, you might add some extra verts if you have like a super massive cube or something that's really big with low poly. For shadows, for the application I'm going to show today, we don't actually have any real-time shadows, but ideally you keep these as low as possible. And I think if I was developing a VR game, I wouldn't even have them on still. I would just put like a little quad under the character, which is sort of what this is showing here, and just have these sort of blob shadows where it's just you just draw a square under the character with the sort of circle texture. Anti-aliasing. This is one of the more interesting things that you'll notice in VR. I really wish I could put a slide on sort of why you need anti-aliasing in VR. It's just sort of something, as soon as you put on a headset, you'll notice that aliasing is so much more of a problem than it is on PC. Like when you're looking at distant objects, you'll just see like these pixels sort of flicker like sort of violently. It's because like when you're holding a mouse, the sort of mouse only moves when your hand does, but in VR you sort of notice these micro movements of your head that sort of subtly make the pixels just um sort of like smear. Um so I reckon with multi anti-aliasing, you have to have it at least 2 times, otherwise your game won't look very good. And you ideally want 4x, but it does decrease your frame rate by about 20 to 30%. Um, and it was one of the most surprising things for me getting into VR, because most of the video games I play, I don't even put anti-aliasing on, but it's just so important for VR. If 4x MSAA is enough or not enough, I wouldn't recommend turning to 8x MSAA. I would just turn up the render scale a little bit, which will render the eye textures or like the camera at a slightly higher resolution, and then downscale it. Increasing the render scale above 1 is very expensive, and there'd be very few games where I think that it would actually be practical to do that. Some more notes on sort of anti-aliasing is, um, if you can, I think the aliasing artifacts, you want to sort of avoid them when you're developing your art assets. So the worst assets are sort of like skinny poles, like things like pipes and like things that are like sticks. Um, Ideally, you want to design your rooms in such a way that you can't see objects too far in the distance. So maybe making your room sort of like S-shaped rather than having long hallways. Um, you could add, if you have like sort of an open environment game, you could add fog, um, and you could also use that fog to sort of color objects that are beyond that fog. And if you have super metallic or shiny objects, then um, they show it the worst. And if you're really far away from those shiny objects, you can turn down how metallic they are to sort of reduce this a little bit. Another Unity setting to get it like a little bit more performance is one of Unity's new technologies, which converts your C# language to C++. It does make debugging a little bit harder and error reports a little bit harder. So I only really recommend turning this on um, when you're finished with the project, and it's slightly that's a mistake there, that it improves compile time. It slightly makes compile time take longer. So because it's just an extra step, it converts your C# code again. So it's just sort of an extra step in the compiling tool chain. I'll just have a quick look at chat. Okay. So this is sort of for the artists where you create your scene. This is sort of on Oculus's website. This is their targets. So you want to keep draw calls between 80 to 600, depending on how much the CPU's doing. So some of the examples they give is like, is your game doing like online networking? Do you guys have like animated avatars in your game? Like, depending on how much is going on in your scene, depends on how many draw calls you'll be able to get away with. And not all draw calls are built equally, so it's kind of just sort of a rough guideline. Same with the triangle count. I would try to keep your scenes under 1 million triangles, or at least 1 million triangles loaded all at once. The scene we have is like I think it's like exactly pretty much 1 million triangles, and it runs well. But as you'll see with our project, it's pretty bare bones in terms of like there's no animations or anything going on with it. So yeah, I'll actually open up the project right now, so we can have a look at sort of what it looks like. And yeah, if anyone has any questions at this point, feel free to chuck them in chat while I sort of put this headset on. I don't know why the analog stick was moving to start with then. So that's, I mean, I guess that's the joy of doing a live demo. So this is the sort of house that we're going to be playing with today. So this is one of our sort of demo houses that we sort of first created to sort of see what can we get running on the Oculus Quest in VR at runtime. So this house runs on the Quest at 90 frames per second, looking exactly how it looks right now. I'm just using a Steamvr headset to sort of show you what it looks like. So yeah, that's what we'll be that'll be the scene that we're looking at today. So the first asset that we use in this project, so that we don't have to render any of the shadows at in real time, is we use Bakery for all our lights. It's pretty popular in the industry. Notably, Call of Duty Mobile uses it, which is like their sort of mobile ported version of Call of Duty. It also works really well with low poly assets. Like you don't need to have realistic graphics to use Bakery. I think it works just as well on low poly and sort of more artistic art styles. Alternatively, you still can use Unity's built-in rendering engine. This is one of the most popular architecture visualization assets on the Unity Asset Store, and this uses Unity's inbuilt lighting. I think it's a little bit hard to get the lighting looking just right using Unity's inbuilt lighting, but with a little bit of work, you definitely can get there. So the last sort of project setup step we'll do is we'll enable occlusion culling. So you just mark all the objects that won't move in your scene as static, and then you can bake the occlusion culling, and this will just make it so that when the camera is looking somewhere, it won't render objects that are outside of the camera's view frustum, which is just sort of like a triangle, sort of where the camera looks forward. So once we've done all this, we get our initial frame rate for our project, which is 48 frames per second, which is definitely not good enough. One of the tricky things with VR is like when I showed this to my colleagues, because they'd already got used to seeing quite a lot of my other VR applications, they actually thought this was really good, running at sort of 48 frames per second. And what this sort of shows is that the more time you spend in VR, the worse judge you become at sort of how well things are at running. Like you always want to be showing your VR stuff to new people and see how they react. Like, can they understand the control scheme easily? Because as developers, we get really used to sort of the frame rate and we get really used to our controls. So I think it's always good to get fresh eyes looking at your projects with VR, more so than like sort of traditional mobile games. So let's optimize. This is the easiest optimization to do, and I think this is one that's just like super magical. Essentially, the edges of our screen will render at a lower resolution than the middle of the screen. So this sort of white area is rendered at 100% resolution. The red areas are rendered at 50% resolution. The green areas are rendered at 25% resolution, and then blue is 12.5, and pink is I don't know what 12.5 divided by 2 is. 7.125, I think. No, 7.625. And I find that even on high, you barely can notice it. On medium, I don't think you can really notice it at all. So you can get like 20 to 30% easy performance improvement just by sort of calling this one sort of C# command. And like I was saying earlier in this talk, anything that you sort of see in Unity here sort of applies to Unreal. So I've also linked the documentation of how to do this in Unreal blueprints. So after our first optimization, we got 30% extra performance, and we're getting really close to 72 frames per second. We're getting really close to sort of turning it into a happy face. One of the things I didn't understand about, didn't really know until really trying to optimize this project is how bad or poor Unity's inbuilt static baking is. So this asset here, what it does is it goes around your scene and renders the camera in almost every single like sort of location, takes a screenshot, sees what pixels, like what objects get rendered, marks them with a color, and then if they are seen, then it will render them, and if it's not, then it won't render them. And it does this for every part of your scene, and you do this before you compile your application. And what you get is the output on the left versus what Unity has on the right. So I definitely would recommend this asset. They don't even actually show it being used for VR, but I use it for VR and it's awesome. Unfortunately, as you'll see later, this house, because there's not really any culling to be done in sort of the worst case scenario, it doesn't really result in that much better performance in this house. But in some of our other houses at work, it results in about 20 to 30% performance gain. An alternative to using this asset would be creating your own occlusion culling system, and this can be quite basic. Like you could just say that your game has like sort of 3 different zones. You just sort of say, if you're in zone 1, render this stuff, in zone 2, render this stuff, in zone 3, render this stuff. And the way that you cull objects would just be to disable their mesh renderer or their game object. And if you're in Unreal, you could just disable their actor. Profiling. So this is like the most important slide in this whole talk, and unfortunately, it's not my slide. I've actually just taken it from someone else's talk. But sort of this very simple flow chart sort of helps you find where you want to optimize. So the first question you got to ask yourself is, am I GPU bound or am I CPU bound? So the quick way that you can do this is disable all the mesh renderers in your scene so the headset's rendering nothing at all. And then you go, well, did my performance improve? If the answer is no, then use some sort of CPU profiler to continue optimizing. If it's GPU bound, then are we vertex bound or are we fill bound? Like, are we? Is the GPU struggling when it's processing all the vertices in our scene, or is it struggling to render all the pixels in our scene? So the way that you can do this, check which of these two it is you can set the render scale, which we talked about earlier when we were talking about anti-aliasing. You can set this to like almost 0, and if the performance improves, then we're fill bound, and if it's not, then we're vertex bound. So if you're fill bound, then you've got to somehow optimize your shaders, which we'll talk about one sort of optimization today. But mainly we'll be talking about this vertex bound because mainly on the Quest, your problem isn't usually the CPU. It's usually the graphics card, but we will talk about some CPU optimizations later. So let's talk about some of the tools that we can use to find some of this information out without having to sort of recompile our game every time. The Oculus VR headset has this tool called OVR Metric Tools. It's super lightweight. I always have this running on my headset. I even accidentally have it on my headset when demoing to people. It's not distracting to use and has lots of useful performance metrics. So it just sort of renders this grid in the middle, and you can fully customize what it shows you. This is like the absolutely everything version of it. So the first thing that's useful that it shows you is the frames per second graph. And you can use this to find areas in your game that don't perform well. So whenever I measure the frame rate, like earlier where I'm measuring it here, this is the absolute worst part of my application. Like at the moment, most of the application is actually running at 80 to 90 frames per second. But if you stand right in the back corner of the house, then it will drop all the way down to 62. So That's how I will always measure frame rate. Is like, what is the absolute worst place in my scene, and that's where I'll spend most of my time. Um, you'll notice that there's also this stale thing, and stale's really important because it shows you how many frames were not rendered. Um, Frames per second doesn't necessarily give you an accurate number of how many frames were measured, and I'll get onto that in the next slide. Um, FOV, this shows you what level of fixed foveated rendering you're running at. So when we went on this slide, um, you can also set it that when you're doing fixed foveated rendering to dynamically change depending on how fast the game's running. So if your game's running super fast, then it won't even render it low. It'll just render the whole headset. So you can see that these values are 0, 1, 2, 0, 1, and 2, and 3. They also have this 4, but I don't recommend ever using that. It's like super overkill. So you can see this value here. It's currently set to 0, so fixed foveated rendering is not on. You can also see this CPU L and GPU L. So this shows you sort of what clock rate the CPU and the GPU are running at. So you can see the CPU L is here and the GPU L is here. So you can see that the GPU is running at its highest level. So this value is between 0 and 4, 4 being the highest. They can't both be 4 at once. So the Snapdragon XR2 sort of prioritizes power between the CPU and GPU, to sort of increase battery life and sort of increase thermal performance. So what are these stale frame rates? Like how do we get higher frame rate than what we're actually measuring? If you don't render a frame in time on an Oculus headset, then the window manager of the headset will actually render a frame for you. So if you wonder how that's even possible, essentially what it does is while your application's running, it's also rendering this time warp frame where it looks at how did the headset move, what did my previous frame look like, and then it will sort of like warp and blend it to generate a fake frame if you can't render a frame in time. So this is actually a really not nice thing, like but it's just something to be aware of when developing. You can use the Unity profiler. Unreal has something very similar, so you can see sort of like how many draw calls, batches, triangles, were there certain areas where it wasn't running as well. Um, there's also this tool called RenderDoc, and this is the one tool that I haven't managed to have a real deep dive into. I've linked a talk done by Oculus on it because they've built sort of like a custom version of RenderDocs specifically for the Quest. It's really useful if you're having performance issues with your shaders and you're wanting to like sort of improve your shaders, or you're not 100% sure how the headset is rendering each individual frame. I think this is sort of like your last resort and sort of like your real deep dive. But I think it's really worth learning if you're sort of a technical artist. I think this is like the tool to sort of improve performance on your shaders, specifically on the headset. Uh, One of Unity's newer tools is the frame debugger, and this tells you why your rendering is not getting batched, like why when you're rendering two different objects, why they're not getting combined into the same draw call. So it will say this draw call can't be batched with the previous one because the nodes have used different shader keywords. So you can see that in this case, like sort of this one adds like sort of a bump map, so it can't like the bump map and the base map are different, so it can't sort of batch those together. Um, Unity's also added in sort of experimental this memory profiler. I've used this for one Windows application before. I think it's very unlikely that you'll use this, but if you're running out of memory on the headset, then this is definitely the best tool to see sort of what is chewing up the most memory in my application. Um, so Unity has this baked lit material, which is a much cheaper shader. So on any non-reflective materials on the scene that are using baked lighting, we use this, and this gets us to sort of the frame rate that I sort of want, where this actually gets us to our sort of like 90 frames per second. Um, if you need to do sort of like any post processing in your scene, like when we do teleporting from location to location, instead of using post processing effects, which are really expensive on mobile devices, you can just draw like put a simple quad in front of the camera, and you just want to change the render queue sort of on that quad so that it always draws on top, so that you can't see like objects sort of clipping through this quad. Um, this is something that I'm on, like I've done a little bit of research into, but I haven't quite implemented yet. One of the other talks I linked to sort of talks about um, doing this, where if you want to have lookup tables, sort of post processing, like you sort of want to change the saturation values, or you want to make the colors pop. Instead of doing it in post processing, you want to create a custom shader that um, does the lookup tables at runtime. I actually want to try with our applications in the long term, take this one step further and see if we can actually do the lookup tables at compile time rather than runtime, because we actually have the flexibility of um, sort of creating this pipeline where once the pipeline's done, we won't need to modify it too much. So I definitely want to see if we can do lookup tables at compile time and actually edit the raw textures and materials. Um, so I'll talk about a few bonus optimizations. Um, if you have large levels in VR, I think Mesh Combined Studio 2 is amazing. So you can see what it's done here is it's created these little cubes, and then it will all the assets that use the same materials, um, it'll combine them into just one mesh, so that you reduce the amount of draw calls, and it can sort of atlas your textures, so that like sort of instead of rendering like 7 individual models, it'll convert them all to one. Um, the alternative to using an asset like this is sort of combining all your meshes when you're building them in Blender or Maya. The problem with doing this is that when you get up to the level designing phase, you can't move objects around because they're all linked together in the same model, like they're all like sort of glued together. So I wouldn't really go with the alternative. I think purchasing an asset like this is really worth the time investment. And most of our houses, we've seen like a 20 to 30% performance increase, just by using this asset, just by sort of using it with its almost almost default settings. Um, so if you're sort of CPU bound, like I was alluded to earlier, here's like sort of some of the asset optimizations that if you're CPU bound. Um, and C sharp, whenever you use the new keyword, um, it sort of puts memory in what's called the heap, and this is like sort of referred to as garbage. Um, if, and this is like really expensive for the headset to deal with. Um, there's a whole page on sort of garbage collection here, and there honestly could probably be its own talk sort of minimizing this. But if you're having CPU bottlenecks, definitely have a look at this page and see what you can do. You can also look inside the Unity profiler under the CPU usage and look at this like sort of scripts section and see if any of your individual C sharp scripts are causing performance issues, and look at optimizing those first. Um, If you still want more CPU performance because you're doing something super expensive, like you want like 10,000 bullets, or you want like 1,000 zombies, or you want lots and lots of stuff, you can use Unity's new data oriented tech stack, or also known as DOTS. It's pretty experimental. I used it for one of my applications at my old job. We had to do queries on thousands and hundreds of thousands of pallets for a client, and I got like, I think I was about 5,000x speed up. So these sort of performance improvements that they show in this talk here, they're not actually exaggerative. You actually really can get performance speed ups of that level, in terms of, this is on just like the CPU basis. This isn't talking about sort of um, how the GPU will cater. Um, so yeah, what sort of can ECS be used for? It can be used for um, when you have lots of vehicles, lots of zombies, or just any other enemies. Bullets. If you have a gun that fires like thousands of bullets, missiles, just anything you have lots of. It also can be used for physics. Unity has its own separate physics built on ECS that runs much faster. And like I said before, I've used it for querying objects of certain types. Um, if you're wondering sort of how this works, like how is it magically like 1,000x faster? One of the main reasons is that if you look at graphs of like sort of CPU performance and RAM performance, RAM is getting much slower than is improving at a much slower rate than CPUs. So whenever you do any compute, you're getting more relevant memory in the CPU caches per compute cycle. You also instantly get like 2 to 4x speed up because you actually start using more than just one core. And then on the individual core level, CPUs have like these special instructions for doing in one compute cycle, um, executing a single instruction with multiple data. So like each core will be computing 8 times as much like per clock cycle. There's a talk link down here if you want to have a look at dots and sort of see how it works. Um, this is sort of like your last final ditch effort of squeezing performance effort out. The CPU and GPU levels I talked about earlier, you can actually manually set these via um, C sharp script, or by Unreal blueprints. Um, so like say in your game, there's like you fire a rocket and it's got like this really expensive fire trail behind it and an expensive explosion. You can set the GPU level to 4 when you fire the rocket, and then once the rocket explodes, you could set the GPU level back to 0. And if you set it to 0, then it will just choose the lowest available GPU level that can render your scene. Um, every talk and every talk I've watched, like sort of talking about performance, says that the CPU and GPU level can't both be 4 at once. I couldn't find any official documentation saying that. But I've never ever seen both at 4, and I've definitely been pushing the headset to its limit. So I don't think it's possible to have both at 4. However, it is possible to have both at 4 if you type a special command using Android debug tools from your PC, um, which is like my last sort of slide on sort of getting more performance, which is like you can use programs to sort of make the Oculus Quest run faster than normal, but you're definitely not going to get it published on the App Store. Users that do this talk about their battery life decreasing by like 30 or 40%, and the device does run hotter. Um, here's a link to every sort of thing that was sort of like mentioned in the talk. They're mentioned sort of at the bottom of slides. And yeah, um, that's it. Oh, here we go. Here's a question. So yeah, if anyone has any questions, you can put them in chat now. Um, Oh, I'm not logged into Twitch to put the link. Got a question from Game Developer Guild. Would it be better to develop a VR project on Unity 2020? I think so. Most of the VR developers I use, I know actually use 2019. I personally use 2020. There's, I would wait for the LTS version to use Unity 2021. If you're wanting to publish it on any app store. Yeah. Does anyone else have any other questions? While I wait for that, I'll just quickly go through the NZ Game Developers Association sort of announcements. We're currently looking for a program administrator. So if you love sort of working remotely and you know lots about video games and you love documentation, then there's a link here. I will put these links in chat in just 1 second. I will quickly log into to Twitch. This Friday, Ubisoft Singapore and Gamescom are presenting Asia at the forefront of gaming from 6 p.m. to 6:45 p.m. New Zealand time. There's an email below if you want to get added to that. If you want to present your game at Armageddon Auckland, COVID permitting, October 22nd to 25th at ASB Showgrounds, there's a Google form for you to apply to. And if anyone's just got any sort of general announcements, feel free to put them in Twitch chat, and I'll read them out. So, yeah, I'll quickly log into Twitch right now and put all these links into chat. How would you approach things like foliage, trees? That's a great question. Let me just quickly put a. You can sort of use billboard, like sort of billboards where you sort of just have two quads rendering like sort of how my hands are showing. It's one of the cheapest ways. The other thing you could do, which I haven't had a chance to do just yet, but I would definitely check out this asset here, Amplify Imposters, because we're wanting to add trees to the background, sort of outside. And this sort of takes things and sort of makes like simplified versions. So like that model there is just 6 triangles at imposters. So it like sort of renders them from like 10 angles and turns them into 2D textures. Oh, so you can see there how it's all the cameras that are rendering it. So here's an example they have of a tree. So try amplified imposters. Would be my advice. Unfortunately, a lot of my solutions are buy something from the asset store, but I think if you try to do any of the stuff manually in Blender or whatever, you're just going to be taking forever to sort of implement this manually. There are also tools to sort of down res some of your assets. Like you can use something like Simply Gone, which I think is I can't remember how its licensing works, but I think it's very cheap unless you're making like millions upon millions of dollars. So sort of you just put sort of your models into it, and it will decrease the amount of triangles, but maintain most of the visual fidelity. They also do have once again optimization for trees. So I'd have a look into both of these, and I think you'll find a good solution. Does anyone have else have any questions or announcements? Would there be an issue with overdraw if you're doing billboards that are overlapping a lot? There would be. Um, yeah. Yeah, you probably want to try like as much as you can, sort of try to like rely on the skybox if you're wanting to sort of have like that layer of depth. Um, yeah, I think the answer is mainly that it's hard. Um, if you're wanting to animate them, you might be able to get away with like using the new VFX graph and using particles if you're wanting to sort of animate them, or just animating them in a shader. Um, but yeah, I think overall you don't want to have lots of trees. Um, wait for the next generation of VR headsets if you want lots. What was the most graphically intense room you designed for a Unity XR project? Honestly, this house is actually really up there for sort of the most graphically intense stuff that I've worked on so far. Like this is the corner right here that is um, really expensive, because you can see it's rendering almost everything in the entire scene when you stand in this corner. Like you have to render all the kitchen. You pretty much have to render the oven, and you have to render absolutely everything. So standing here is not ideal. I think as we move forward, as I sort of build the pipeline to sort of support bigger and bigger houses and sort of automate the pipeline so that any house can just sort of automatically be um, converted to sort of a VR ready. Some of the really expensive houses have very open floor plans, which are just a nightmare for rendering efficiently. And I don't have the luxury of saying redesign the house so I can render it faster. For the light, um, I'm actually struggling to log into my Twitch account right now, Josh. So I'll just quickly send you all the links if you can just put them in chat. For some reason, my Twitch is not wanting to agree with me. Why is this pasting as a picture to you? Oh, let's try copy something else. For the light map for the house, are you using multiple light maps or a single big one? I think I'm using about 8 4K light maps. So there's definitely more than one. I render at we look at bakery. We're rendering at sort of in this one we're rendering at 200 texts per unit, but now we're sort of for most of our houses we're doing 150. Um, I don't know why when I copy and paste everything, it's just pasting it as a link and not copying the text. I've never seen anything like this. When in doubt, type it out. Um, I'm glad I shortened the link. So if anyone has any other questions or announcements, just chuck them in the chat. I'll stay here for another 5 or 10 minutes, and then we'll. Have you looked at Google's? No, I have not. It sounds familiar. It does sound familiar. I'll actually open that up. This is this link word that I sent. Cool. Google. Let's have a quick look at it. Is this like their? This isn't their like rendering of like. I think I have seen this. Is this like they use like cameras to sort of make this like sort of 3D visualization thing, and they have like they have these 3D depth cameras now in their offices that let you do like 3D video calls. Yeah, I have seen this. Um, I don't know much about it other than it's really cool. Yeah, I've seen demos of this where they take videos of real life footage. Um, oh yeah, I'm definitely really curious to see how sort of technology like this evolves. I'm really excited that we're starting to get these VR headsets that have like AR pass through, and the Quest just added that. I'm really hoping that the new version of the Quest, I'm hoping one will come out this year that will have sort of like color pass through. But yeah, there's so much happening. I see today that there's this VR headset that you're meant to wear while sleeping. It's called like the Half Dive. I have no idea what it's about, but later on tonight I'm gonna have a look into it. Because I don't understand why you'd want a headset while sleeping, a VR headset. It doesn't make any sense to me. I'll quickly bring it up while I wait. Wait to see if there's any other questions. Well, that's what I thought. It's going on Kickstarter, I think next month or something. Dive, world's first bed-mounted display VR headset. Um, oh, it's going to have varifocal lenses. Well, that's the first VR headset that I've heard of having varifocal lenses. Essentially, these all the current VR headsets, you're always focusing at sort of like a fixed distance in front of you, where varifocal will actually adjust the lenses so that far objects, your eyes will actually change focus between far objects and close objects. They use this using like sort of polarizing liquid crystals. Um, that's a lot of money to spend on a headset, $4,000 US. But I don't know what the purpose of this is. Um, but I'll find out tonight. Oh, yeah, I think we'll wrap up there. Oh no, what was the frame debugging like on old versions of Unity? Um, is it, I'd love to know if I'm answering your question properly, because when I used older versions of Unity for frame debugging, it's pretty much the same as like the Unity profile has existed in this sort of state for a long time, but you haven't had things like this frame debugger and this memory profiler. Um, I'm actually relatively new to a lot of this optimization stuff. Most of my programming typically has just sort of been mono behavior. I have not worked with the Quest on Unreal Engine, unfortunately, but I've seen quite a lot of tutorials. Is Universal Render Pipeline best for phones? I think it is. If you have an existing project and it's almost done, I wouldn't switch pipeline. It's kind of like universal render pipeline. The main downside with it is you have to learn a few new things, and if you're using custom shaders, then they're not going to work coming across. You're going to have to recode them. Universal render pipeline is developed so that it can target everything. I should actually show you one other quick picture about universal render pipeline. Um, this is the house above with a few extra post processing effects added to it. This is our company website, and you can have really beautiful scenes using universal render pipeline. This is all universal render pipeline, and we've added things like screen space reflection, so you can see the ground is now like super reflective. Unfortunately, you cannot have screen space reflections running on the Quest. You can actually sort of see this aliasing issue that I'm sort of talking about, sort of on this tap, just here. But I don't see why there'd be any issues using UE 4.27. I know 4.27 is the first version of Unreal Engine that supports OpenXR, and I know that OpenXR being sort of the standard where if any game implements OpenXR, then the application will work on any OpenXR headset, and all headsets are becoming OpenXR headsets. And I know that the Oculus Quest 2 is already officially supports OpenXR. So I'm assuming 4.27 is the latest version of Unreal. I think it is. I think it's the one that came out like a month ago, isn't it? Or was it 4.28? 4.27 came out. Yeah. So yeah, I can't see any reason why it wouldn't work. I think it would work really well. And there are quite a lot of tutorials. I have seen quite a few tutorials for doing Quest optimization in Unreal. Did I answer your question about sort of what frame debugging was like on old versions of Unity? I'm hoping that answered your question. It's pretty much the same as today, but there's just less tools for the job. Oh, if you guys have any further questions that you come up with after this, feel free to send me a message on Discord or Twitter. Oh, there we go. There's the links. I believe these slides, this video will also be uploaded to YouTube later under Joshy's YouTube account, which is also on the Auckland Game Dev Meetup page for this talk. I believe it will get uploaded there afterwards. Thank you so much, everyone, for joining in, and hopefully I'll see you guys in person in the near future at the Auckland Game Dev Meetup. Bye.